Welcome to Coffee Cup Calorimetry calculations. I will be going through some sample problems from 5.2 to give you an idea of how to solve these problems. And as we go through them, I will try to reinforce some of the concepts that you've been learning about simple calorimetry. So let's begin. We're going to start with number 22 of your practice problems on page 305. And number 22 reads, when 5.022 grams of sodium hydrogen carbonate reacts completely with 80.00 mils of acetic acid, the temperature increases from 18.6 degrees Celsius to 28.4 degrees Celsius. Assume that the acid solution has the same density and specific heat capacity as water, and that the mass of the final solution is 80 grams. Calculate the molar enthalpy of reaction. So it is always good with these types of problems if you begin with what is given. And you are given that you have a mass of sodium hydrogen carbonate of 5.022 grams. This is your system. And it is reacting with a volume of 80.00 mils of your acetic acid. Now, because this is a dilute aqueous solution, we consider the water that makes up that solution to be our surroundings. And this is how we do our enthalpy calculations. We're looking at the change in heat of the surroundings and then applying it to the system. So because we see that the volume is 80.00 mils of the acetic acid, that it is a dilute solution, we are going to assume it has the same mass that water does. And the density of water is 1 gram per mil. So for every gram of water, or every mil of water, it weighs 1 gram. So 80 mils of water would weigh 80 grams, and then 80 mils of this dilute acetic acid solution would weigh 80 grams. And we are also able to calculate delta T, which is the final temperature minus the initial temperature. And that's 28.4 degrees Celsius minus the 18.6 degrees Celsius, which gives us 9.8 degrees Celsius. Now we can use that information and we can plug it into our heat formula, which is Q equals mc delta T, or also known as mcat. And we will put in the values for water. For the mass, we're going to assume that our acetic acid has the same mass of water, and that is 80 grams. We use the specific heat capacity of water, which is 4.19 joules per gram degree Celsius, and our delta T, which was calculated at 9.8 degrees Celsius. That gives us a value of 3,284.6 joules. Now this is the heat that the surroundings, the water, acquired. And we know that it is opposite of the system. The system must have lost that heat or given up that heat to the surroundings in order for the surroundings to be that. So we say the enthalpy of the system is equal to the negative Q of the surroundings. And we can say that the delta H of the system is negative 3,284.9 joules, which is also equal to negative 3.2849 kilojoules. And we will convert it to kilojoules because that is how often how many of the units are used in this system of calculation. If you remember the conversion factor from joules to kilojoules, for every kilojoule, there are 1,000 joules, and that's why we can change the value in that way. Now we will plug that information into the following formula to get our molar enthalpy. Molar enthalpy is a change in heat per mole of substance in our system. Now we don't know the number of moles yet, and we have to go back to our mass of sodium hydroxide. And we can calculate the number of moles from mass by taking the mass and dividing by its molar mass. If you remember, we did this last semester. And we plug those numbers in, take 5.002 grams of your sodium hydrogen carbonate. Once you calculate the molar mass, remember that would be adding together 1 mole of sodium, 1 of hydrogen, 1 of carbon, and 3 of oxygen. That gives you 84.01 grams per mole. And when you solve it, you get 0.0597786 moles. Now we can take that value, our change in enthalpy value, and put them into the equation on the right. When we do that, we'll take that negative 3.284.96 joules, divide it by our 0.0597786 moles, and we get a value of negative 55.0 kilojoules per mole. And that is the molar enthalpy of this reaction. We're going to move on to the next problem. And I chose it because it is a reaction with 2 dilute aqueous solutions. It's number 24 of 5.2 in your practice problems, page 305. And it reads, in a simple calorimeter, 25 mils of a 0.120 moles per liter barium chloride solution is mixed with 150 mils of a 0.2 mole per liter sodium sulfate solution. A precipitate of barium sulfate forms. The initial temperature of the 2 solutions is 20 degrees Celsius. After mixing, the final temperatures of the solution is 20.49 degrees Celsius. Calculate the enthalpy of reaction in kilojoules per mole of sodium sulfate. Assume that the solutions have densities and specific heat capacities equivalent to those of water. Again, you will find it very handy if you write down what is given. So in this one, we are given that the concentration of barium chloride is 0.120 moles per liter. And the volume of it is 250 milliliters. We will go ahead and right now and do the calculation for the number of moles. And remember that the number of moles equals the concentration times the volume. When we put our concentration value in and our volume in, remember your volume has to be in liters in order for the units to cancel. And going from 250 mils to liters, you move the decimal point 3 places to the left, and that gives you 0.2500 liters. And your final answer is 0.0300 mole. Now we're going to do the same for the sodium sulfate. We have our concentration of 0.2 moles per liter and our volume of 150 milliliters. Again, the formula for number of moles equals concentration times volume. We put our values in, remembering to convert milliliters to liters. So 150 milliliters becomes 0.150 liters. And we find that we get 0.0300 mole. Again, and it's a 1-to-1 ratio. This is important because if you look at the chemical equation that you were given in 24, the reaction occurs with barium chloride and sodium sulfate in a 1-to-1 ratio. So we can use the value of 0.0300 moles in our calculations. It is important because if there is a difference in molarity and the number of moles, then we have to take that into account because then there will be a limiting reagent. If you remember from last semester, for example, if we had 0.03 moles of barium chloride, but 0.04 moles of the sodium sulfate, they would no longer be in a 1-to-1 ratio, and the barium chloride would become the limiting reactant, and that's what we would have to take into consideration for the rest of our calculations. We also can calculate a change in temperature. But the initial temperature was 20 degrees Celsius being subtracted from the final temperature of 20.49 degrees Celsius. You notice that the temperature has increased, so this is going to be an exothermic reaction. And that temperature difference is 0.49 degrees Celsius. We can take that information now and put it into our formula, Q equals MCAT. Now the mass that we are going to use is going to be the combined mass of the volumes of barium chloride and sodium sulfate. Now, we can assume in these types of calculations that they are going to have the same density as water, therefore the same mass as water. So 250 plus 150 mils would be the same as 250 grams plus 150 grams to make your total mass. And then you'll also use your specific heat capacity of water. So that is where you get the mass from. You're adding basically the volumes, but you're converting them to grams. And you're doing your specific heat capacity of water times that temperature change. When you put that in your calculator, you get 821.24 joules, which means your liquid in your solution has gained thermal energy. And because it has gained thermal energy, the system has lost heat from it. It's the opposite. So we gave it a negative value, and we convert it to kilojoules. And remember, that involves moving your decimal place 3 places to the left to go from joules to kilojoules. We can now plug it into our formula for molar enthalpy and take the enthalpy of the reaction divided by the number of moles. So we take that value of negative 0.82124 joules and divide it by the 0.03 moles, and our molar enthalpy of the reaction is negative 27.4 kilojoules per mole, indicating that it is an exothermic reaction. Now, we will go on to another example question, and that is number 27. And the reason I chose this one is because it works backwards from what we have been doing so far. So number 27 in the textbook reads, the enthalpy of solution for sodium hydroxide is given as negative 55 kilojoules per mole. A chemist prepares 25 mils of a 0.1 molar solution, mole per liter solution of sodium hydroxide. Assuming that the solution has the same specific heat capacity and density as water, by how much should the water temperature increase as the sodium hydroxide dissolves? So, again, it is very helpful if you list what is given. And we know we are given the enthalpy of solution, and it's in units of kilojoules per mole. So this is our molar enthalpy, and it's negative 55 kilojoules per mole. We also have the concentration of sodium hydroxide and the volume of sodium hydroxide. So we can go ahead and calculate the number of moles by multiplying the concentration times the volume, remembering to put all the units in the same kind. So converting your milliliters again to liters for a total of 0.0250 moles. So once you have that, we have used the formula. Molar enthalpy equals that the molar enthalpy equals a change in enthalpy over the number of moles, but we have to rearrange it now because we have the delta HR, we have N, but we don't have delta H. So we have to multiply each side by N, and we get now our change in enthalpy is going to equal N times the molar enthalpy. So we put in our value of number of moles, we put in our molar enthalpy, we get a value of negative 1.375 kilojoules, but we want now to calculate for Q, and we know it's the opposite sign. So all we have to do is change that sign, and Q is positive 1.375 kilojoules. And now we can go to our formula, Q equals MCAT. And because we are looking for a change in temperature, we have to rearrange this formula. So we're going to rearrange it by dividing both sides by MC. That gives us a delta T of equal to Q divided by MC. And then we put in our numbers and we solve. And we find that the temperature has increased by 1.31 degrees Celsius.